All right, so the next of our tests for convergence and divergence is what is called the alternating series test. This is relatively a straightforward test. It's not too difficult to understand how it works, and the criteria are not too bad. The most difficult part is showing one of the criteria, which is the decreasing part. So this is what the alternating series test says. An alternating series is a series that alternates between positive and negative signs. Kind of makes sense. Um, the big thing with that is that it must alternate every term, positive, negative, or negative, positive. You cannot go positive, negative, negative, positive, positive, negative, negative. That's still a pattern. It's just not considered an alternating series. So the alternating series test is good for positive terms. So your a sub n needs to be positive, and we're going to qualify something with that. So if you have the series, negative 1 to the n, a sub n, the a sub n part here, this part has to be positive. Obviously, this negative 1 to the n is going to alternate the terms, so the terms are going to go back and forth between positive and negative. Or you could have negative 1 to the n plus 1, which just means you're going to start instead with an even positive term and then a negative term and so on. An alternating series is going to converge if the following two conditions are met. And it's just two conditions, and they're relatively straightforward ideas. The limit of the absolute value of the a sub n. Now, it's kind of weird to say that because this right here is a sub n. It should already be positive. What it really means is the absolute value of this. So basically, ignore the negative 1 to the n part. If you take the limit of that and it approaches 0, that's the first condition. The second condition is that this a sub n, ignoring the negative 1 to the n stuff, that's why it's in absolute values, must be decreasing. In other words, the next term has to be less than the previous term for everything. Hopefully that makes some kind of sense. So every next term must be decreasing, and the limit has to approach 0. So let's look at this graphically real quick. If we were just to look at a sub n without it being an absolute value. So you might have a term that starts here, and then because it's got to be decreasing, the next one might be here, and then 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 here. So you can see it's decreasing and getting closer and closer and closer to 0. The absolute value, here let's label this, this would be like a sub n. The absolute value of a sub n, instead of having all of these things down here below, are going to be up here, but it's just going to form a pattern that looks something like this. So it'll be here, then here, then here, then here, then here, and so on. And it's going to approach 0. If one or both of these two conditions up here fails, then you can use the nth term test with a sub n to determine if the series diverges. So this will only tell you convergent, it will not tell you divergent. So if it meets these two conditions, the series will be convergent. It does not tell you divergent if one of these fails. We're going to try a different test. All right, let's go ahead and get to it. We should be able to get through all of this stuff, I think, in one video. Let's see. Determine the convergence or divergence of the sum negative 1 to the n plus 1, 1 over n. This is obviously going to be an alternating series because of the negative 1 to the n plus 1. So let's run through our tests. We want to take the limit as n approaches infinity of the absolute value of a sub n. Well, if this whole thing right here is considered your a sub n, then the absolute value of that is just the 1 over n part. So we'll take the limit of 1 over n, and of course that approaches 0 as n goes to infinity. So that's the first criteria, check. A sub n also has to be decreasing. Or excuse me, the absolute value of a sub n must be decreasing. Must be decreasing. This one is obvious. There's no real work to do here because the absolute value of a sub n is 1 over n. as this numerator gets bigger, as the denominator gets bigger, the numerator stays constant. So the bigger the denominator, the smaller the fraction. So this is going to be true for all n. A sub n is decreasing for all n greater than or equal to 1, and it starts at 1, so we're fine there. Therefore, it met both criteria. We have a convergent series. Okay, criteria 1 was met here. Criteria 2 was met here. Okay, pretty straightforward in something like this. It's where you have things where you've got numerators and denominators to think about how it's working to determine the decreasing portion of it. That's where it gets a little more challenging. Like this one. Okay, determine the convergence or the divergence of this series right here. So if we take a look, first thing we're going to do is we're going to look at the limit. Because it's alternating, and I can tell that it's alternating, we're going to go straight to the alternating series test. No need to try anything else yet. The limit of the absolute value of this, well, the absolute value of this is just going to be n plus 1 over n, because the absolute value takes care of the negative 1 part. You don't have to worry about that. And that limit, of course, is 1. Well, that's not 0. This is not 0. This is inconclusive for the alternating series test. So we have to try something else. What it says to do is it says to use the nth term test, which is just strictly the limit as n approaches infinity of this thing without taking the absolute value. So now we're talking about the whole thing with the negative 1 to the n plus 1, n plus 1 over n. So as this thing approaches infinity, well, the larger and larger the numbers get, this thing is still going to bounce back and forth between negative 1 and 1. This part here goes to 1, so what's going to happen is this thing is going to go to 1 or negative 1 infinitely. It's going to bounce back and forth. Therefore, the limit here does not exist. And if we use the nth term test and the limit doesn't exist, that means it's divergent. Remember, the idea behind the, whoops, what happened? Lost my pen. The idea behind the nth term test was that if you get anything divergent, if you get anything other than 0, it's divergent when you take this limit. So we're done. We got 1 or negative 1, which technically means it doesn't exist because you can't have two limits, therefore it doesn't exist. Okay, let's take a look at this one. Again, this is negative 1 to the n right here. So we know it's going to be an alternating series, especially because n starts at 3. Natural log of 3 minus 2 is natural log of 1, which is 0. So this thing's only going to get bigger from there. This will always, these terms here will be positive. This negative 1 to the n is going to change that, so it will be alternating. So let's go ahead and take the limit as n goes to infinity of the absolute value of this, which is ignoring the negative 1 part. And as n approaches infinity, this natural log is going to go off to infinity, and so is this denominator. So we're going to get an infinity over infinity form, which means we're going to need to use L'Hopital's rule. Okay, L'Hopital's rule, the derivative of the top of this is going to be 1 over n minus 2 times the derivative of n minus 2, which is 1, over the derivative of the denominator, which is 1. And we really don't have to worry about that. So really what I'm taking is the limit as n approaches infinity of 1 over n minus 2, and of course that approaches 0. So there's the first criteria met. Second criteria is not as easy in this case. The numerator and the denominator are changing. Okay, and that's going to make things a little bit more challenging. So what we need to do, and we've done this kind of thing in the past, we need to let f of x equal natural log of x minus 2 over x minus 2. And to show that this is going to be a constantly decreasing function, we need to take the derivative. So f prime of x, let's see, the derivative of the top, 1 over x minus 2, times the bottom, x minus 2, minus the derivative of the bottom, which is 1, times the natural log of x minus 2, which is the top, all over the denominator squared. All right, and we want this to be less than 0. We want to find all the x values where this is less than 0. Well, this x minus 2 squared is never going to be 0. I'm sorry, it'll never be negative. So we don't have to worry about this. We can kind of get rid of this part. So really we're just talking about the numerator. The nice thing is here 1 over x minus 2 times x minus 2 is 1. So I'm going to have 1 minus the natural log of x minus 2 has to be less than 0 in order for this to work. All right, so I can algebraically I can add the natural log to the other side. Oops, not equals. Is less than natural log x minus 2. In order to solve for this x minus 2, we're going to have to use exponentiation here. So if I exponentiate, what that's going to give us here is e is less than x minus 2. And then solving for x, we're going to add 2 to both sides. So e plus 2 is less than x. So as long as x is bigger than e plus 2, which is approximately 4.7 something, so anytime x is greater than 4.7, or technically because 4.7 cannot be an n value, remember we're going back to the n idea, as long as n is greater than 4, this is going to be okay. So what we can say, because this started at 3, it's okay that it starts at 3. From 4 on, this will be a convergent series. So for n greater than 4, a sub n is decreasing. Therefore, this is a convergent series. Okay, remember, the first couple of terms don't really matter. It could be that it goes from increasing to decreasing, but it's what happens at the extreme of this thing. As n approaches infinity, it must be constantly decreasing. Okay, that's the important part. All right. Number 4 here, let's see. Determine the convergence or divergence of this series. Once again, I see a -1 to the n, which means this thing is going to be alternating. I've got a 3 to the n over n plus 1 squared. If I were to look at the limit as n approaches infinity of the absolute value, so that's 3 to the n over n plus 1 squared. The best thing to do here is to compare the growth rates of these things. If they were both polynomials, it'd be easy. The idea is that this is exponential, this is polynomial. Exponentials are going to grow faster than polynomials. That's always going to be the case. So this one is exponential, this one is polynomial. The numerator is going to grow faster than the denominator, therefore this thing is going to go to infinity. Now, if you weren't sure about that, because both of these technically are going to go to infinity, you would do L'Hopital's rule. And as a matter of fact, I think you'd have to do L'Hopital's rule twice here because of this second power. right here. But you would eventually get that the numerator keeps growing while the denominator stays constant, which is going to lead you to infinity. And since this goes to infinity, and I've taken the limit, this is divergent. So we kind of skipped right to the nth term test right there, even though we were trying to do the alternating series test. Because if I throw a negative 1 to the n out here, it's not going to change the fact that this is going to go off to infinity. It's just going to bounce back and forth between infinity and negative infinity. So one way or the other, it's going to keep getting bigger in the positive or negative direction. All right. Example 5, determine the convergence or divergence of negative 1 to the n plus 1, natural log of n over n. So let's take the limit as n approaches infinity, absolute value of our series, which is the natural log of n over n. Both of these go off to infinity, so if you use a L'Hopital's rule, we can do this in one shot. The derivative of the top is 1 over n. The derivative of the bottom is n. So you get 1 over n, and of course that goes to 0. And again, if you think about this in growth rates, a linear function is going to grow faster than the natural log. If you know the graphs and you understand how that works, that's always going to be the case. A polynomial is going to grow faster than a log. That's just the way the graphs work. So this would definitely go to 0. All right. In order for us to show the decreasing part, f of x is the natural log of x over x. Let's take the derivative. So the derivative of the top is 1 over x times the bottom, which is x, minus the derivative of the bottom, which is 1, times the natural log of x, all over the denominator squared. We want that to be less than 0. This is very similar to the problem that we just did. This x squared is never going to be negative, so the numerator is going to determine everything. And that numerator 1 over x times x is going to be 1 minus natural log of x. We want that to be less than 0. Adding the natural log to the right, we get natural log of x has to be bigger than 1. Well, the natural log of e gives you the 1, so as long as x is bigger than e, and if you didn't know that, you'd exponentiate both sides and you would get this. As long as x is bigger than e, we're good. E is about 2.7. We don't even start this thing until n equals 3, which is great. So that means for all n, so as long as n is greater than 3, a sub n is decreasing. Therefore, both criteria have been met, and we have a convergent series. Wonderful. All right, moving right along. Determine the convergence or divergence of this one right here. So these things look like they grow at approximately the same rate, which tells me that once I take the limit of this thing, because we're going to do that anyway, the limit of the absolute value of n plus 1 over 3n plus 1 equals a third. Okay, that fails the first test. It doesn't equal 0. Well, if you take the limit of this thing with the negative 1 to the n plus 1 attached to it, this is going to go to either positive or negative 1/3. Which of course means that the limit is not going to exist. Sorry, that's a 1. So this is going to go to plus or minus 1/3, which means the limit doesn't exist. Therefore, this is divergent by the nth term test. Like I said, these are not terribly difficult to do. Okay, it should be pretty clear to see on this one right here. Once I get rid of this negative 1 to the n, the denominator is going to grow faster than the numerator, so the limit will equal 0. We'll write it down. Just so that we have it written out. That's 0. There's the first test. Now we'd have to do the derivative so that we can tell when it's decreasing. And hopefully this thing is. It looks like it probably will be, but we'll check it and see. Derivative of the top is 1 times the denominator minus the derivative of the denominator, which is 2x times the numerator, all over the denominator squared. Again, we want that to be less than 0. This thing here is never going to be less than 0, so again, it's the numerator that's going to cause our function to be positive or negative here. So let's see, this is going to be x squared minus 2 minus 2x squared minus 2x has to be less than 0. This is going to give us, what is that, negative x squared minus 2x minus 2 has to be less than 0. So I can't think of a number where that's not going to be the case. The easiest thing to do is this. Let's multiply everything through by a negative sign. Remember, when you do that with an inequality, it changes the direction of the inequality. So really what we want is we want for all of these x's, whatever we plug in here, it doesn't matter, because remember all these x's have to start with 3 or more because they're technically n's. So anything from 3 or higher, this is always positive. So this is going to be the case for all n. For all n, a sub n is decreasing. Therefore, this is convergent. All right. That is the alternating series test. What we still have to talk about is one more thing, and this is what is called the alternating series estimation theorem. We can't actually find the sum from this, but what we can do is we can estimate how good our approximation is going to be. And it's basically what is called the remainder theorem. The alternating series remainder is another way to think about this. So the idea is this. If you were to take the sum, the actual sum of this thing, well, the sum would actually be taking the actual sum of the entire series and adding it up. That would be the sum of an alternating series. The problem is we obviously know that that's not necessarily the easiest thing to do. What we need to do is we need to look and see if the sum satisfies these conditions. First of all, it's got to be alternating. Okay, that has to be true. The next term, the b sub n plus 1, has to be less than the previous term. Okay, that's got to be one of the criteria. And then the limit of the b sub n has to be 0. This is the exact same thing. This means that you have a convergent alternating series. If this is the case, all this is just saying we have a convergent alternating series. If this is the case, the absolute value of r sub n, this is what is called the remainder, is equal to the actual sum minus the sum of the first n terms. Let me kind of illustrate that right here. So if I have an alternating series, starts here, then goes here, then here, then here, then here, then here, and so on. Well, let's say that this is the first n terms, like the first 4 is what we're going to call n. So we're going to cut it off right there. So if we added up all these first 4 n terms, well, that is going to be this s sub n. That would be the sum of the first n terms, however many we decided it to be. We'll call that n. The remainder has to be the entire sum, which is all of this stuff out here added up as well as these terms right here, minus this first n terms. So the entire sum of the whole thing minus the first n terms gives you the remainder. This stuff out here is what's left over. This is your remainder section. So let me kind of put this in here. Out here is the remainder. This is the sum of the first n terms. If I take all of these things right here and add them up, then I would actually get the entire sum. So the remainder is going to be the entire sum, the whole red part, minus the green part. That's the remainder. Well, this remainder, and this is the important piece of this remainder is less than or equal to the next term in the series all the time. This is the next term right here. That's the next term. This remainder is always going to be less than or equal to this term right here. See how everything gets smaller and smaller and smaller, closer and closer to the to 0? It will always be less than this next term. So that's what we're trying to say. So let's put that in words. The size, ooh, that's horrible. I'm not doing very well writing right there. Try again. The size of the error in our sum, meaning the remainder, is smaller than b sub n plus 1. That's the next term, which is the absolute value of, and this is what we call it, the first neglected term. So think of it this way. If I told you I wanted you guys to find the error, or the greatest error of an alternating series, but I wanted to do the alternating series with 17 terms, you're going to look at the 18th term and say, okay, whatever that 18th term is, that is the biggest possible error in our series. Or if I said I want you to find the error of the first 7 terms, or let's use some different number like 10 terms, you would look at the 11th term and say the error is got to be smaller than that 11th term. That's the general idea. So what we want to do in this case is we want to find the sum of this correct to 3 decimal places. What we need to do is we need to create a partial sum. So let's do that. So the sum of the first so many terms, I don't know what it's going to be. But let's see, if I start with n equals 0, negative 1 to the 0 is 1 over 0 factorial. That's defined to be 1. So 1 over 0 factorial, that'll end up being 1. The next term, if I plug in 1, will give us negative 1 to the first, so that's negative 1 over 1 factorial is 1, plus plugging in 2 is going to give me a positive, so that plus is good, positive 1 over 2 factorial. It's going to alternate, minus 1 over 3 factorial, 1 over 4 factorial, and so on. That pattern is going to continue. Our job is to figure out how many of these terms it's going to take before the third decimal place stops making a difference. It's kind of a tedious process. So what we're going to do is we're going to actually simplify these. So this is 1. That's also 1. That's a half. 3 factorial is 6, so that's minus a sixth. Plus 4 factorial is 24, so that's 1 over 24. And what I'm going to do is I'm going to add up these terms and see what I get. Okay, from this I got 0.375. That's from adding up these first 5 terms. So now I'm going to go ahead and I'm going to figure out the next term. I'm going to change this to red now. So the next term would be minus, because this was plus, so it's going to be 1 over, see, 5 factorial is going to be 120. And now I'm going to take it, I'm going to add up all of these terms, and we're going to see what we get. And after I plug that in the calculator, I got 366 or 367, depending on if you're rounding. As you can see, the third decimal place is still changing. It went from 5 to 6, so I haven't gotten far enough yet. So let me go, let's go with blue. Let's go out another one. That would be plus, let's see, that's going to be 6 factorial, which is, I believe, 720. And we're going to see what this is if I add 1 over 720. And we get 0.368. It's getting close because now in this case the 6 has stayed constant in the second spot, but this 6 here did still change. So I'm thinking maybe one more term might not actually affect this third decimal place. Let's find out. I'm going to keep it in blue just because I don't want to keep changing. Minus, oh boy, what is that going to be? I'm going to have to plug this in the calculator. 7 factorial is 5040, and yes, I had to plug that in the calculator. I did not know that one. So we're going to subtract 1 over 5040, and when I do that, again, this is just doing partial sums here, that's going to give me 0.368, rounding. So the first, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, the first 8 values, which is going to be the sum of 1, 2, 3, 4, 5, 6, 7, S sub 7, I guess. The first 7 terms are going to be what this sum is, and then it doesn't change when you get to here. And actually, if you took just this value right here and just figured out what this thing is, 1 over 5040, actually let me do that. 1 divided by 5040 is let's see, 1 over 5040 is less than, now in the calculator it gives 1.984 to e to the negative 4, which means it's a scientific notation, which means this thing is actually 0.0002. And what you should see is that third 0 here means it's not going to affect this spot right here. So that means that I could have just looked at this term right here and said, oh, well, this term is 1 over 5040. It's 0.002. It's not going to affect my third spot because I'd be adding 0 to the next number. So in this case, this is the first neglected term. So what my sum is 0.368 with an error or remainder of less than 0.0002. Okay, not necessarily the easiest concept, but hopefully you'll get to understand it. You're going to have to do a couple of practice problems on these, I'm sure. So there is the alternating series error or remainder theorem.